Hello everyone. In this video lecture, I will talk about mass spectrometry. So I have already talked about few spectroscopic method which is indeed required in the experimental synthetic lab and also in order to understand different chemical processes. I have already discussed NMR spectroscopy, UV spectroscopy, absorption and fluorescence both. Now I'll talk about mass spectrometry. Now, what is mass spectrometry? Mass spectrometry is the separation of ions, atomic or molecular, according to the mass to charge ratio. So basically in this spectrometry, in this spectroscopic technique, we are going to separate ions. The ion can be atomic ion or molecular ion. Means, for example, sodium in a plus or potassium plus, it may be atomic ion or whole overall molecular ion. Means overall molecule, it is positively charged or negatively charged according to the mass to charge ratio. Now a variety of mass spectrometric techniques is available, and we focus on electron ionization, or what we can say electron impact technique, fast atom bombardment, matrix assisted laser disruption ionization, time of flight, and electrospray ionization method, all of which are routinely available. So there are different technique, mass technique, of which we can detect the mass of your sample. So first one is the electron ionization EI. Then I will talk about fast atom bombardment FAB, matrix assisted laser disruption ionization, that MALDI, and ESI MS. So most commonly these technique are used in order to assign the mass of the analyte. First coming to EI, that electron ionization method. So you can see that this is a schematic diagram of an electron ionization or electron impact uh, mass spectrometer. So this is a basic design. So in electron ionization mass spectrometry, ions are produced by bombarding gaseous molecule with high energy electron. So you can see that here sample is ejected, and sample actually from the sample ions are produced by bombarding high energy electron. Now it is a hard technique because in this technique molecules are getting fragmented. The parent molecule are fragmented in their smaller part. So this is schematic representation of EI mass spectrometer, which is shown over here. As you can see that the the compound may be solid, liquid, or gas, and it is introduced into the instrument. It is introduced to the instrument, as you can see from the this diagram. This sample inlet is injected through here. The now heating zone. This is the heating zone where the molecule, where the sample is heated and it is vaporized. Now when the vapor is generated, this vapor is subjected to a stream of high energy, naturally 17 electron volt energy of electron, which are bombarded, which ionizes this sample. So when this vapor is produced, it is subjected to a high energy electron volt. High energy electron is bombarded with this vapor, so that the ions are produced. Now the molecular ion is which is normally written as capital M in third bracket over positive charge, and is radical cation, and is strictly written as capital M within third bracket plus, is shown over here. You can see that this is the scheme is given over here. The molecule, the sample is shown over here, M within bracket gas, in gaseous state. So first sample have to be in vapor phase. So whatever state you put the sample, liquid, solid, or gas, after the heating zone it should be produced, it should be in vapor phase, and then it is bombarded with high energy electron, and you can see that it is produced in this molecular ion peak. This capital M plus is the molecular ion peak. This is strictly written as in this form, radical cation form. energy of electron used for the bombardment is much greater than the covalent bond energy and thus causes fragmentation of parent molecule. What happened is that in EI technique, the energy is used is much higher than the covalent bond energy of the molecule of the analyte, and therefore fragmentation takes place. Thus, in addition to the molecular ion peak or parent ion peak, which is actually capital M plus, in mass in mass EI image fragments are also produced for. Therefore, this electron ionization technique, mass spectrometry, is called as or classed as hard technique. Hard technique, so because in this technique, along with the parent molecule, molecular ion peak, we are also getting fragmented part of your molecule. Now, after the positive ion is produced, it is passed through a magnetic field. You can see that it is passed through a magnetic field where their paths are deflected. The amount of deflection depends on the mass of the ion. The larger the m by z value, the larger the radius of the path of the ion follows. So the output from the mass spectrometer of a mass spectrum normally is plot of signal intensity against mass to charge ratio. So what is the ultimate fate when you detect the mass spectrum? It is plotted against the signal intensity versus m by z ratio. I will show you in the next slide, couple of slide, the mass spectrum, experimental mass spectrum. For a now for an ion having z is equal to 1, that is charge is equal to 1, the m by z value is same as that of molecular ion. But if your charge is 2, for example z value is 2, then the recorded mass spectrum is half of the actual mass spectrum, because m by z, whatever your mass is, when you divide with z is equal to 2, the m by z, that is the m by z value will be half, and so on. So in the EIS mass spectrometry, most ions have z is equal to 1, but you also get the fragmented part also. In the mass spectrum, the signal intensity is plotted in terms of relative values, with the most intense value, the base peak, it is called base peak, being arbitrarily assigned as a value of 100%. So in the next couple of slides, I will show you in the mass spectrum the most intense peak, which is 100% abundance. It is called as base peak. It may or may not be your molecular ion peak, but it is arbitrarily called as the base peak. One addition point is that the fragmentation pattern, the appearance of a mass spectrum depends upon the natural occurring of isotopes of the element. So the natural isotope of the element actually giving that pattern in the mass spectrum. The presence of several isotopes of an element. For example, an element has several isotopes, and that leads to an observation in the mass spectrum, that pattern, which is called the peak envelope. I will talk about in this kind of peak envelope in the later part. Now coming to our first worked example, this is the mass spectrum of of the molecule, small molecule POCl3. This is the phosphorus shown in the orange color, double bond oxygen in red color, and then 3 chlorine atom shown in the green color. So the POCl3 molecule, and the mass spectrum you can see that shown over here. The x-axis is the m by z and y-axis is the relative intensity of this mass value, m by z value. Now you have to assign the peak in this EIS mass spectrum of POCl2 molecule shown below. Now first, in order to assign, you have to know that the mass of this chlorine, phosphorus, oxygen and their relative abundance in nature. What is the isotopic pattern, isotopic abundance in nature? Then you need to calculate the mass of POCl3 molecule as a whole, and then you have to fragment them in order to match their masses as shown in the mass spectrum. So this is the abundance. You can see that isotopic abundance of this phosphorus, chlorine, oxygen atom. Phosphorus is 100% 31p form. Chlorine, there are two isotopes, 35 chlorine and 37 chlorine, and isotopic abundance is that 75.77% is the 35 chlorine, and 24.23% is 37 chlorine. In case of oxygen, there are four isotopes, but mostly there are three isotopes. Uh, but you can see that the oxygen 16, you can taken it as a 100% false. 16 oxygen 16, mass number oxygen 16, which is abundance is 99.76%. You can take it at 100%, which close to 100%. So because chlorine has two isotopes and these two isotopes has significant abundance, the mass spectrum exhibits a group of peak, and this group of peak actually called peak envelopes. You can see that this group of peak, whenever you see this group of, you see that at around 120 region there is a group of peak, at around 160 region there is a group of peak. Now this group of peak suggests that this peak envelope, because of this isotopic abundance, different isotopic percentage, they having different values in the mass spectrum. Now first determine the mass value, that is m by z value for the peak that you are expecting of your parent molecular ion M plus peak, using the most abundant isotope. Now you can see that the molecular ion peak for POCl3 molecule, POCl3, you can take the most abundant form of the isotope 31p, oxygen 16 and 35 chlorine, and if you calculate all these mass of phosphorus, oxygen and 35 chlorine, you will see that m by z will coming out to be 152, for z is equal to 1. Of course, molecular ion peak here, charge is 1, that is why you are getting the whole mass. M by z value is 152. You put the 31, 16 and 35 into 3, you will get the m by z is equal to 152. Now you can see that these matches the left hand peak in the group of highest mass peak in the mass spectrum. So if you look carefully, you will see that 152 is there in the mass spectrum. So this around this region, you can see at the right hand side, at most right hand side, around, you just look at around 160 region, there are four peaks. This is first one is from left side to right side. First one is 1552, second one is 154, relative like intensity is similar, close to similar, then very small intensity is 156, and then very small peak which is for 158. Now this peak correspond to which molecule, which ion, you have to understand that part. Now this peak envelope, this is called a peak envelope, and this is coming because of this isotopic pattern, isotopic abundance of chlorine and of chlorine. You can see that the first peak at 152 is for this molecular ion peak. I have already shown you the calculation, 31p, 16 oxygen and 35 chlorine into 3. The second peak, you just replace 135 chlorine to 37 chlorine. So you will get additional 2 mass unit higher number, 152 to 154. Now you change 2 chlorine atom to 37 chlorine atom. So you can see that the third mass number is actually 156, which is for 31 phosphorus, 16 oxygen, 135 chlorine and 237 chlorine. Then the last peak, you replace all 3 chlorine atom, 35 chlorine atom with 37 chlorine atom. You will get 158 peak, which is very small intense in nature. You can see that. So all these mass are matching with this analysis. This actually matches the left hand peak actually. Now coming to the peak around this 120 region, you see that the peak envelope, there are three set of peak is there around 120 region. The first peak, which is the highest in intensity, the value is at m by z is equal to 117, 117 value. Second one is 119 and third one is 121. Now this is for the fragmented part. You clipped one chlorine atom, then it will give PoCl2 plus. Now this PoCl2 plus, if you calculate the mass for phosphorus 31, oxygen 16 and 35 chlorine into 2, you will get this 117 peak. Now because of chlorine has isotope, two isotope, you replace one chlorine atom with 37 chlorine, you will get this 119 peak. You replace two chlorine atom, 35 chlorine atom to 37 chlorine atom, you will get this 121 peak. So this kind of peak around 120 region is for the fragmented part, PoCl2 plus. One chlorine atom is clipped. You can name this kind of peak can be written as M minus Cl plus. The M is for molecular ion peak, minus Cl means one of the chlorine is clipped. So this is the designation how to write this kind of fragmented peak. Now the peak around this 80 region, it is for the cleavage of two phosphorus chlorine bond. So this peak around this 80 region, there is two peak, it is for PoCl, one phosphorus oxygen on one chlorine, and because of the chlorine has two isotope, you will get this two set of peak. You can replace 135 with 137 chlorine, so you will get this two peak. Now the peak around this region 66 region, m by z value, this is for this is because of M minus 2Cl minus O, means two chlorine atom is clipped along with the oxygen atom. So there is one phosphorus chlorine bond, one phosphorus chlorine unit is there. So that is why you are getting these two kind of peak because of the two isotopes of chlorine. You can replace 135 with 37 chlorine and you will get this M by Z is equal to 66 and you will get this two isotopic pattern. And this peak, which is single ion single peak, which does not have any isotopic pattern, this must be free from chlorine, that is it is for M minus 3Cl, means this is for PO fragment only. All the three chlorine atom are clipped from phosphorus center, that is why you are getting this one kind of signal. There is no isotopic pattern because no chlorine atom is there, so you are getting a single peak. And the remaining peak, like at m by z is equal to 31, it is for the atomic ion peak, phosphorus. For phosphorus ion, it is giving this 31, and this two peak, smaller two peak, it is for 35 and 37 chlorine. So this peak around this below 40 region, this peak is coming because of this atomic ion peak, atomic ion. For chlorine, you are getting two peak, 35, 37, and for phosphorus ion, you are getting at m by z is equal to 31. So overall, you can understand that all the signals are matched with our observation. We have analyzed it. The right hand side around 160, it is for the molecular ion and its corresponding isotopic pattern, isotopic distribution pattern I have talked about. The peak around 120 is for the fragmented part, one chlorine atom is clipped from the phosphorus center. The peak around 80 is for the cleavage of two chlorine atom, and peak around 66 region is for the three chlorine atom which two chlorine atom which clipped along with oxygen. The peak around the single ion peak, which is corresponding to cleavage of three chlorine atom, and it is only contains PO moiety, and the remaining part below 40 is for the atomic ion peak. Now coming to the another technique, it is called fast atom bombardment, or in short FAB. So in this technique FAB, ions are produced by bombarding the sample. The sample may be neutral molecule or ionic salt with the high energy xenon source or argon atom. So in the last EI method, electron ionization impact method, there you can see, there I have shown you that the atoms are bombarded with high energy electron. Here atoms are bombarded with high energy xenon or argon atoms. It is called a soft technique and usually causes little fragmentation. In this fab method, normally there is a little fragmentation as compared to the EI method. Now this fab mass spectrometry was developed in the year 1980s and has a number of advantages over EI. I will tell you one by one what is the advantages of this technique fab. So first one is the molecular masses up to 10,000 can be determined. So high molecular mass you can determine in this method, whereas in case of EI you will get the most of the fragmented part, molecule will get fragmented. So the molecular ion peak for the higher masses you will not get as a base peak or higher intensity peak. The instrument can be run both in positive mode and negative mode, so therefore you can get the both positive ion mass value and negative ion mass value also. Again, you can take the ionic salt or neutral compound as your analyte and you can investigate their mass pattern. Unlike EI, in this fab method, fab technique, it is a soft technique because the fragmentation of the parent molecule is usually minimal. Minimal amount of fragmentation takes place in this fab method. Now coming to the setup part, principal part, how to uh, um, uh, operate this technique. So the sample to be this is a schematic representation of the component in this fab mass spectrometer. As you can see over here, different part is shown over here. Now the sample to be analyzed is mixed with high boiling point liquid matrix. First of all, your sample, your analyte has to be mixed with high boiling solvent matrix. That compound high boiling liquid matrix normally contains such as glycerol or 3-nitrobenzyl alcohol. Normally glycerol or 3-nitrobenzyl alcohol. Now this in this matrix, glycerol matrix or 3-nitrobenzyl alcohol matrix, your sample has to be put. Yes. Now this mixture is applied to the probe of the instrument and it is bombarded with fast xenon or argon atom. So you can see that this argon gun, argon atom is bombarded over here, high energy xenon atom beam, and this is your probe. This is your matrix, liquid matrix probe with sample lead plate. Now after the bombardment, these ions are getting generated, and these ions are called these ions are getting generated, and it is passed through this beam, and it goes through the analyzer part. So these are generated in an atom gun by ionizing xenon. Now xenon will be xenon plus, so argon will be argon plus, like it will get be ionized, and then accelerating the ions in an environment where electron capture occurs to given stream of atoms with energy less than 10 kilo electron volt. Now this beam of atoms, each matrix sample produced with the energy close to 1 electron volt. Now there are certain part when the instrument is run in positive mode, the atom bombardment of the sample leads to different fragmentation, and when it is run in the negative ion mode, it is gives some different component which needs to be analyzed in order to understand the fab method. Now I'll come to that part. Instrument is run in positive mode, you will see that a direct release of parent molecule, that is a molecular ion peak, from an ionic salt mx minus or overall mx positive, overall mx plus, like ionic salt, from ionic salt. So one of the thing is that from ionic salt, direct release of the your cationic peak, molecular ion peak, positively charged peak. Now combination of the neutral molecule with cationic, usually proton or Na plus. So in your mass spectrum you will get the peak corresponding to the M plus H or M plus Na plus. So your neutral molecule will combine with one proton or one sodium ion to give that Mh plus or Na plus ion. Also ions such as M minus H plus. So it can also be possible that one of the proton is clipped, so you will get that M minus H peak. Aggregation may takes place to form that 2m plus H and 2m plus Na plus, this kind of thing. Or also your molecule, your molecule can be in the matrix itself with the protonated form to give this kind of aggregated form. So in the positive mode, you have to analyze all this possibility. Your molecular ion peak can also be in the form of M plus H form, M plus Na form, and also M minus H form. Now when the instrument is running negative mode, atom bombardment result in different kind of phenomena as shown over here. So you can see that combination of a neutral molecule with an anion. So if a neutral molecule in the negative ion mode, it will combine with the anion for let's say Cl minus or H minus to give M minus M plus H minus or M plus Cl minus. So it will combine with this anion H minus or Cl minus to give this combination pattern in your mass spectrum. Also the proton loss to give M minus H this peak, aggregation to form M2M minus H, this kind of peak. So the origin of Na plus and Cl minus, this kind of cation anion in this Fab method maybe impurities in the sample, but NaCl may be added to the analyte. Sometimes NaCl may be added to the analyte in order to generate that kind of combination peak. The ions leaving the probe are said to be structured, and the beam of ions is focused for entry into the mass analyzer. In the last diagram I have shown you the ion that are actually generated by bombarding the xenon atom. These are called these structured, and the beam of ions, this beam of ions is focused for entry to the mass analyzer. Now you read the question carefully and try to analyze by your own, and then you can check the answer. So the question says that when a PPH3 gold chloride reacts to this compound, rhenium hydride compound, and the product is treated with KPF6, a yellow crystalline solid is isolated. In the Fab positive ion mode, the mass spectrum exhibits peak envelope at M by Z is equal to 2135, 1845, and 1582. So there are three peak are getting generated in the Fab positive ion mode. Now so that these data are consistent with the product being formed, the product is given as over here. You can show that this is a ionic compound with a cationic part, and this gives it anion, and assign all the peaks. The structure of this cation part is core shown over here, cationic part is shown over here. You can see that. So this is the overall molecule. uh, Gold, this is actually rhenium. This white color is the rhenium which connected to 4 carbonyl. This CO oxygen is red in color, this carbon is as shown in the ash color. So this 4 carbonyl rhenium, and it is connected to 4 gold atom which show in blue in color, 4 gold atom. And you can see that this phosphorus over here, this yellow color phosphorus, it is shown over here, phosphorus, and pp3 attached with it, which it is not shown. So this is overall the code structure. Now there is 3 mass is given: 2135, 1845, and 1582. So now if you calculate the cation part, so in the Fab positive ion mode, the cation part will give your molecular ion peak, mass peak. So if you calculate the molecular ion peak for this cation that contain this pH3 gold 4 rhenium carbonyl 4, you will get that value 2135. You put all the value mass of phosphorus, gold, rhenium, carbonyl, you will get that value 2135. Now the other two value, it is for the fragmented part. Now if you analyze carefully, if you clip one carbonyl and if you one carbonyl and one pph3 group, because in the positive ion mode, Fab mode, it is very likely to keep one of the carbonyl or triphenyl phosphine group. So if you calculate the one pph3 and carbonyl group, you will get that value 1845 peak, and that 1582 peak, 1582 peak is corresponding to the cleavage of two triphenyl, two pph3 group, and one carbonyl. So basically it is, you can written it can be written over as shown over here: M minus pph3 minus carbonyl, overall positively charged, which for 1845 this value, and M minus 2 pph3 minus carbonyl, this ion is corresponding to 1582.8 this m by z value. So you can see that the overall molecule gives that 2135 as the molecular ion peak. This is the base peak. The other two value in the positive ion mode, it corresponds to the fragmented part. The 1845 value corresponding to the cleavage of one triphenyl phosphine, one carbonyl moiety, and the second value 1582 corresponding to the cleavage of two triphenyl phosphine and one carbonyl moiety. Thereby it matches with the experimental data. Coming to the metric assisted laser disruption ionization time of flight MALDI-TOF. So in metric assisted laser disruption ionization time of flight, which is known as MALDI-TOF mass spectrometry, normally a UV laser is used to generate atoms or ions in the form of M plus H or M plus Na ion are typically detected in this technique. It is a soft technique because there is a little fragmentation takes place. So in the metric assisted laser disruption ionization MALDI, as mass analyzer uses a pulsed UV laser beam to produce ions for mass analysis. Now this MALDI, when it's coupled with TOF, time of flight mass analysis, provide a sensitive technique which is especially useful for very high molecular mass compound. For molecular weight as big as 30,000 or more than that, 3 lakh, around 3 lakh, including biomolecules and polymers. So biomolecules, polymer you can detect in this MALDI-TOF technique. The sample is mixed with large excess of matrix. So the sample is to be mixed in the matrix which is capable of absorbing this UV light, UV photons. For that, these two compounds normally used in the matrix preparation, this hydroxycinnamic acid and synapic acid, this kind of molecule are used for the matrix preparation, and the matrix analyte is to be loaded onto the sample plate. In the sample plate, the matrix and analyte is to be loaded where it crystallizes. The energy is provided by the pulse UV and it is absorbed by this matrix form, causing the disruption of the molecule of the sample. In a combination with proton or sodium ion normally produce this M plus H ion or M plus N ions, and in since MALDI is a soft technique, there is usually little fragmentation of the parent molecule takes place. Multiply charged ions are rarely formed. So multiple charged ion, the other technique I have talked about, there are chance of multiple charged ions. So here it is rarely formed. This is a schematic representation of the components in the MALDI-TOF mass spectrometer. You can see that this is a matrix sample shown in the red color. The sample is embedded in the matrix, and this is on the plate, sample plate. Pulsed UV laser beam is used of the wavelength of 337 nanometer, and when it is bombarded, it will produce this ion, and it is passed through this beam and goes to the goes to the detector part. This is the top part, time of flight part, and this is the MALDI part. Now coming to the third example related to this MALDI-TOF technique. This is one of the mass spectrum of MALDI-TOF is shown over here, positive mode of a sample of this polydimethyl siloxane elastoma. This is basically a polymer compound. The repeat unit of which is given over here. This Me2SiO unit is a repeated unit. It is an overall polymer, cyclic oligomer basically. The main spectrum is given in the blue part, this blue color. The main spectrum is accompanied by the subspectrum in red. Also there is a red part, as you can see over the spectrum. The spacing between these two consecutive lines, this between two blue lines or between two red lines, if you can see that the consecutive spacing is for m by z is equal to 74. Now rationalize the appearance of the mass spectrum. You have to analyze the mass spectrum. So this is an example of MALDI-TOF technique, and that this is a repeated unit of this polymer, and the spectrum is given over here. Now if you can see that the spacing correspond to m by z is equal to 74. It is basically mass of is one of the unit Me2SiO unit. So this is basically a monomer part. The value of m by z correspond to an Me2SiO monomer unit. Therefore, the series of a blue peaks arise from this polymer chain of different length. So this kind of peak signals, they are basically coming from the polymer chain of different chain length. So with increasing and decreasing of this monomeric unit Me2SiO unit, the signals are getting varied. Similarly, for the set of red peaks, similar also for the red peaks also. Now, this observation of two series of indicates that both the cyclic oligomer and the linear chain is also present in the mass. But however, the intensity ratio, if you can observe that the blue signal are much more intense than the red signal, so thereby you can understand that relative intensity, from this relative intensity, the cyclic oligomer dominate over linear chain. Normally, a cyclic oligomer has the formula Me2SiO whole twice n as given shown over here. But for the particular chain length of linear oligomer, it has a higher molecular mass than that of cyclic part because it is terminated with the terminal methyl or OH group. So the understanding is that the mass spectrum, it is for the polymeric part, and the spacing is corresponding to the one of the monomeric unit Me2Si unit. So you can see that the logical reason of this mass spectrum of this multi-top technique, the spacing is corresponding to the monomeric Me2SiO unit, and the red signal is for the uh, minor amount, the linear chain part, but the blue signal is for the oligomeric cyclic oligomeric part, and the spacing is corresponding to this Me2SiO monomer. In the last part, I will talk about electrospray ionization, that is ESI mass spectrometry. So in electrospray ionization, ESI mass spectrometry, ions are produced from a fine spray of solution under an applied electrical potential. It is generally a soft technique used for both neutral and ionic salt. Singly or multiple charged ions are produced. Observe. So this is schematic representation of the component in the ESI mass spectrometer. The injection of the sample dissolved in a volatile solvent, normally acetonitrile methanol solvent is used, and it is a volatile solvent. Then this solvent of your analyte compound is vaporized. Is vaporized first is that the sample is dissolved in a volatile solvent, acetonitrile or methanol, and the solution is converted into fine spray, nebulized at atmospheric pressure by the application of high electric potential. So by the basically this kind of high 3000-volt potential difference, using this potential, high energy potential, the solvent, analyte and the solvent part is actually converted into fine spray at atmospheric pressure. The SIMS mass spectrometer can be operated both in positive ion mode and also negative ion mode, which produces negative ion mode, and electrical potential is applied between this needle through which the sample is injected and the counter electrode. So after the potential difference is created, though, so this ion are getting converted into fine spray, and they are actually uh, moving towards this gas phase ion pass through this mass analyzer part. They move through this counter electrode part. So an electrical potential is applied between the needle through which the sample is injected and a counter electrode. This basically counter electrode part is there shown in this orange color. This is a counter electrode part. The charged droplet travel towards the counter electrode, during which the time of solvent evaporates. So basically the solvent is actually associated with the charged molecule. During this uh, time it travels toward the counter electrode, the solvent actually gets evaporated. The gas phase ions so formed, now this gas phase ions so formed, it passes through the mass analyzer, and zoom scan of the peak is shown over here, output of the one of the mass spectrum, ESIMS mass spectrum with the relative intensity and m by z value. You can see that. Now, one or two point is important regarding this ESI mass spectrum. Uh, is that if the let's analyze this complex ruthenium bipyridyl PF6 complex, ruthenium tries bipyridyl ligand. BPY is the 2,2 bipyridine ligand. The ruthenium BPY whole thrice PF6 whole 2. This is the complex, and the ESIMS mass spectrum of this complex is shown over here. Y-axis is the relative intensity of the mass, and x-axis is the m by z value. Now, if you carefully analyze this mass spectrum, you will see that the base peak or highest m by z value peak with the relative intensity, the 715 is corresponding to the ruthenium BPI whole thrice PF6. That means that you can rewrite this form as m minus PF6 ion. One of the PF6 is getting terminated. In the mass spectrum, you will get ruthenium BPY whole thrice along with PF6. So it will give mono positive charge or single charge species, positively charged species. The structure is shown over here. This ruthenium in red in color, and this 3 is the bipyridine ligand, 2 does bipyridine ligand, which binds this kind of bidentate fashion to the metal center, and one counter ion PF6 minus is outside the potential sphere of the complex. So overall, as a whole, this is positively charged, single positively charged, and it is giving this mass spectrum over here with the m by z value is equal to 715. And the mass envelope, the isotopic pattern, it is quite interesting to note how it is getting formed. The pattern of this peak is largely controlled by the fact that ruthenium possesses 7 naturally occurring isotopes. Because of this ruthenium, it has isotope, natural isotope, 7 isotope. You are getting this kind of pattern 1 2 3 4 5 6 7, and this difference I have already discussed, this 7 on 3 7 on 4 7 on 5 7 on 6 7 on 7, this spacing is 1 unit apart, and this 1 unit apart suggests that the molecule that is formed, the ion is formed, it is singly charged, positively charged, not doubly charged. If it is a doubly charged species, then you will get the separation 1 by 2 or 0.5. Let's try out this what example related to ESI mass spectrum. So this is the ESI MS mass spectrum is shown over here of a protein molecule ubiquitin of protein molecule. This figure shows an experimentally obtained mass spectrum for this protein molecule ubiquitin. So you have to using any pair of peaks from the figure, calculate the molecular weight of ubiquitin and its percent error compared to the theoretical monoisotopic mass of 8560 m. So basically the question says that from this mass spectrum of this protein molecule, you have to calculate the molecular weight of the protein and calculate the percentage error compared to its theoretical value, that is 8560 mu. Now, for calculating the mass, molecular weight or charge state of a species using the ESI image mass spectrum, there is one formula. I have already told you that charge states you can understand by the difference between the peak position. I have already told you the mono ionic charge or mono positive charge or a dipositive charge you can understand by their peak position, peak separation. If it is 1 unit apart, they are monopositive charge. If they are 1 by 2 unit apart, they are basically dipositive charge, dicationic charge. So this is the formula. uh, Z is the charge state of your species, of your analyte. For that you have to calculate m2 minus a divided by m1 minus m2. M2 is that your your mass of your m by z value, your mass of your desired peak, minus a. A is basically the mass of the attack time, which is normally the proton, which is the mass of normally proton, and m1 minus m2 is the difference between these two species, consecutive two peaks. Uh, molecular rate is that you can calculate by using this formula, m1 minus a into m2 minus a divided by m1 minus m2. The parameter is given, shown over here, written over here. mw is the molecular weight, m1 is the m by z value for the uh, higher mass unit, z is the charge state, m2 is the m by z value for the second ion of lower m by z value, and a is the mass of the attack time, which normally proton, sometimes it may be Na plus or K plus ion, depending on the nature of the method you are using. Now, how to calculate the molecular weight using this figure? So you can take any two peak, and using the second formula, you can easily calculate the molecular weight of this peak. So molecular weight, then you can calculate using this 77983 peak, which is the highest intensity peak, base peak, and the corresponding left peak, that 71492. You would differentiate these two peak, and you will get that value 188566 mu. That is the molecular weight of the compound experimentally. And what is the percentage error? 8566, that is the experimental value minus the theoretical value divided by theoretical value into 100%. So which gives you that 0.07% of error of the experimental to that of theoretical value. So from this mass spectrum, ESI image mass spectrum, one can calculate the molecular weight of your species and also the charge state of your analyte. Now for the molecular calculation, you have to take any two successive peak, their difference, and using this formula you can get that experimentally determined molecular weight of your compound, of your analyte. This is the last example of ESI image mass spectroscopy. This is the ESI image spectrum for cytochrome C electrospray from mixture of water, methanol, and acetic acid with pH of 2.5. The mass spectrum is shown over here. So the question suggests that what is the charge state of the peak at m by z is equal to 773.36. So basically this peak, this you can see that there's highest intense peak 773.36, that is the base peak. What is the charge state of that peak? So basically the ion, the molecule, the analyte which giving that peak, what is the charge state that giving that highest intensity base peak? Also you have to calculate the molecular weight of this protein molecule, of the cytochrome C, using this mass spectrum. Again you have to use that simple formula. From that you can easily calculate that charge state of your species and also the molecular weight. For the charge state calculation, you take that species mass by m by z value, which is given over here 773.36, and you subtract with the adapt proton minus 1.036 divided by m1 minus m2, two successive mass value like 773.36 and this 727.94. You will get that value of your charge species. So you can so it is given so so you can see that what is the charge state of the peak at m by z is equal to 773.36. So for that you have to take 77.36 and the corresponding mass, corresponding like its adjacent signal for 727.94. You just using these two value, you will get that the z is equal to plus 16. That is, it is charge is plus 16 of this biological protein molecule, cytochrome C molecule. Now you can see that in the upper part you are using 7 to 7.94, and lower part you divided these two mass values, and it is basically because of that you have to balance the charge, also the calculation part. You have to similarly for if you want to calculate that 7 to 7.94 peak, you have to do the same thing using the two adjacent peak, and you have to calculate the same manner. So now calculate the molecular weight. For the molecular weight calculation, you take any two peak in the solution state. So basically any pair of peaks can be used. An example solution is shown below, using the peak 773.36 and 7.94, and using the equation you can calculate the mass. So basically m1 minus m2, and the A is basically the proton mass of the proton 1.01. So you will get that value 12360 atomic mass unit, that is the mass of the cytochrome C molecule. So so now in this way you can calculate easily the charge of your species, of your analyte, and the molecular weight. For that you have to take two successive mass value, their difference, and using this formula you can calculate that molecular weight and also the charge species. Thank you.